Hey, have you ever really looked at the shirt you're wearing? I mean, forget the color or the style for a second. Just the fabric itself. It feels so simple, right? But it's actually a marvel of high-speed engineering, all born from one single, incredibly powerful, and perfectly timed motion.
I mean, just watch this loom go. It is an absolute blur of what looks like chaos, but it's completely controlled. And right at the heart of all that action is one single powerful push. It happens again and again with insane precision, hundreds of times every minute, slamming each new thread into its final home.
So, that's the big question, right? How on earth does a machine take a simple spinning motion and translate it into that perfectly timed, super powerful push that you need to create the flawless fabric we all wear every single day? Well, to answer that, we've got to look at what I like to call the mechanical heartbeat of the loom.
This core action is called the beat up. And yeah, it's pretty much exactly what it sounds like. It's this quick, sudden, forceful movement that pushes a new thread, that's the weft, into the main body of the cloth. It's one of the three foundational motions of all weaving.
And the beat up has two critical jobs to do. First, obviously, it has to shove that new thread into the exact right spot. But just as important, it's also responsible for compacting all the threads together to create a really dense, strong, and uniform piece of fabric.
So, let's zoom in. Let's break down the anatomy of just one of those pushes. How is that incredible force actually created?
The real magic here is in a surprisingly simple crank mechanism. Okay, so it all starts with a rotating crankshaft. That's connected to a crank arm, which then moves this pivoting lever called a sleeve sword. And right at the very top of that sleeve, you've got the reed. It kind of looks like a big comb, and that's the part that does the actual pushing.
So here's how it works in motion. The crankshaft just spins and spins in a constant circle. This pushes the crank arm, which makes the sleeve sword swing forward and then pull back, over and over. And every time it swings forward, that reed slams the new thread right into place.
So what you get is this really elegant conversion of energy. You're transforming a constant spinning motion into a precise back and forth swing. It's a simple idea, mechanically speaking, but it is incredibly effective.
But okay, this is where it gets really, really clever. Because engineers have figured out how to tweak this simple movement to get unbelievable speed and efficiency out of it.
And that creates a classic engineering puzzle. The beat up has to be fast and powerful, right? But the machine also needs that whole assembly, the schley, to stay back long enough for the shuttle to fly across and insert the next thread. So how do you balance those two totally opposite needs?
The secret, believe it or not, lies in a single number. The Schley eccentricity ratio, or SER for short. It's just the ratio between the crank's radius and the length of the arm connecting it to the Schley. By just tweaking this one little number, engineers can totally transform how the Schley moves. And it's a classic trade-off. If you increase this ratio, you get two huge wins, a much more powerful beat-up and more dwell time at the back for the shuttle to get through. But there's always a catch, right? A higher SER means faster, jerkier acceleration, and that puts a ton of stress on all the parts, which means you need a stronger, beefier, and of course, more expensive loom to handle.
And this graph shows you exactly how it works. It's so cool. A high eccentricity ratio, that's the lower L over R value they show here, it changes the Strauss's velocity from a nice smooth wave into this sharp lopsided curve. You see that really sharp peak? That's the faster, more powerful snap forward. And that much wider valley at the bottom? That's the longer dwell time at the back. It's the exact asymmetrical motion you need for super high-speed weaving.
So a higher SER gives you a more powerful beat up, which is great. But what happens when that push becomes a little too powerful? Well, you run into a problem called bumping. This is what happens when the beat up is so incredibly forceful that the tension in the finished part of the cloth actually drops all the way to zero for just a split second. The whole fabric just goes slack, and you can often hear this distinct noise as it snaps taut again.
And you can see exactly what's going on in these graphs. The one on the left shows normal conditions. You see the tension drops, but it always stays above zero. Now, look at the graph on the right. When you get bumping, that whole peak of the tension curve is just gone. It's completely cut off. The line flatlines at zero, and that's the moment the fabric goes slack.
And here is the total paradox. You'd think that a more forceful push would always be better, but bumping actually reduces how effective the beat-up is. It's a sign that the fabric structure has basically gotten jammed, and you've pushed way past the point of efficiency.
So how do you solve this? Well, the answer is just as clever. And it kind of brings us full circle to this idea of hidden complexity in everyday things. The solution to bumping isn't to just push less hard. Nope, it's to actually increase the tension on the main lengthwise threads, the warp. By doing that, you give the whole system a bit more give, so it can absorb that powerful beat up without the cloth ever going slack.
And as this quote really highlights, all these design choices have very real consequences. A loom that's engineered for this kind of speed and power has to be built tougher. It needs a more rigid frame and more robust parts, just to handle the immense forces and vibrations without shaking itself to pieces.
So, the next time you pick up a piece of clothing, just remember this. Every single one of those threads is locked in place because of a perfectly balanced conflict, a tiny battle fought between incredible speed, immense force, and material tension, all optimized over centuries of brilliant engineering.
It makes you wonder, doesn't it? What other simple objects in your life, things you use every day, are hiding a similar story of complex engineering and invisible forces, just waiting for you to notice?